I'm going to talk about certain heat kernel estimates. So the starting point or the motivation is the following. If you take Brownian motion and you look at the heat kernel, which we all know it's a Gaussian heat kernel, and you look at short time, then the asymptotics tell you something about distances. In particular, you have this kind of limit. That is an easy computation. And in fact, this extends to more general diffusions. So if you have a diffusion, say, elliptic to avoid, uniformly elliptic, then there is a notion of distance which is associated with a Riemannian metric related to this matrix of coefficients. And Varadan, many years ago, proved the same type of result. Namely, the short time estimates reveal the geodesic distance between points, and the asymptotics is of the same type. So the exponent, the t here is the same exponent for such diffusions. And there are lots of generalizations of that. This is related to large deviation theory, and I wrote some names, but you could write here 25 other names and you would not be doing much injustice to the topic. Now, a particularly simple case is a case in which sigma is just a scalar. So this is just a time change. And for the time change, you can represent your process as a Brownian motion time change by some additive functional. In this case, the additive functional is along the trajectory. And very similar results hold. Of course, it's a particular case of the previous one. Now, since I can take any time change, I can take the exponential of something, and in particular the exponential of a Gaussian field. Then the time change begins to look like something that, if you were not completely asleep in the last 2 days, you have already seen in several versions. And in particular, the equilibrium measure for this kind of object is this one. Okay? So all that works when v is kind of a smooth function, so that 1 over a is neither explodes nor goes to 0. And what we want to do is, of course, to do the same in the situation where v is not such a nice function. In particular, we are going to assume v to be Gaussian and to have a correlation structure of this form. So log correlated in 2 dimensions. And for reasons that will become clear later, I would like to add some freeness to modify this log by a bounded perturbation. Okay? So, of course, the Gaussian free field is in that. Now, some reminders. We can define an approximation of v, for example, by modification, and then the sequence of measures given like that converge, if your gamma is not too large, to a measure given in this form. And this goes back to Kahan, and there have been a lot of contributions of people in this audience and in various degrees of generality. So the equilibrium, what I called before the equilibrium measure for our diffusion, is well defined. Now, of course, there are lots of things that are relevant for this equilibrium measure. So let me just mention them quickly. So, of course, the total mass is uniformly integrable. The measure itself is supported on certain class of thick points, which are points in which the values of the approximation are atypically large. The limiting measure does not depend on the modifier you used. All these properties, by the way, hold for this perturbed Gaussian free field. So you should not think of the Gaussian free field as the only case where you have this kind, although some of the constructions, for example, by martingales, don't necessarily work once you add the perturbation. And And I want to emphasize this last point, a lot of things are universal, namely they do not depend on the particular perturbation you use. For example, the dimension of the thick points, so that's a Hausdorff dimension. It does not depend on the approximation. The epsilon maximizers, their existence, their limit law, etc., all that does not depend on the particular class of approximation, or not only on the particular class of approximation, but in fact on the actual field you use. So now let's go back to the diffusion exercise we discussed in the beginning. So given this measure, you can try to define a Brownian motion by introducing this object. Okay, that's a time change that we saw earlier that will relate the Brownian motion to a new process, which hopefully is a diffusion. Now, of course, because V is not defined pointwise, what is written a priori does not make sense. Okay, but on the other hand, we are smearing things out by an integral from 0 to t, so you could think that exactly in the same way that the measure exists, maybe this object also exists in an appropriate limit. And in fact, this was proved a few years ago by Garban, Rhodes, and Vargas, and independently by Nathaniel Berestiki. And the result of Garban, Rhodes, and Vargas is that there exists a strong Feller diffusion xt, which continuous path that correspond to 1. And in fact, they identified the Dirichlet form for this process. And the Dirichlet form is the one you know. The only difference is the domain. So you are able to integrate different functions with respect to this Dirichlet form. So, okay, so this is now very tempting to try to use the hit kernel and deduce some information about the structure of space, in particular about geometry. I already should tell you we are not able to do that. We are very far from that. But still, if you hope that someday you can do something like that, then you should begin by being able to say something about the hit kernel. So a general paradigm in the story of diffusions on fractals and on other irregular graphs is that the hit kernel should look something like that. And by something like that, so there's usually a polynomial prefactor, and then there's an exponential term, and the exponential term has both the distance and some power of t. And in fact, in general, there are only two parameters. Excuse me. Two parameters. One parameter, which is the polynomial power in here, which is called up to a factor of 2 the spectral dimension. And the other is the parameter that comes up here, which, as you can see, because this ratio is dh over b, there's one number which is called the Hausdorff dimension. I should emphasize that this is not necessarily the case that the hit kernel should look like that. In fact, there are examples where other exotic behavior is observed. In particular, you could have here different objects, you could have logarithmic terms, etc. But this is kind of a paradigm where these numbers, their name come from this paradigm. Now, of course, for Brownian motion, everything behaves like we think, namely the spectral dimension is d, is the dimension of the ambient space, whereas the Hausdorff dimension is 2. Okay. Sorry? dh, yes, the Hausdorff dimension is d, yes. Sorry. Okay. So a little bit after proving the result on existence of the Liouville Brownian motion, Rhodes and Vargas settled the question of the spectral dimension. In particular, they proved that it is 2 in the following weaker sense. So the weak sense is that you don't look at directly this pre-exponent or this on-diagonal behavior, but you take this limit, and the reason is that the upper and lower bounds actually had extra log factors, and you could not actually prove a result about p multiplied by. And in fact, these log factors were somewhat improved in a paper that came shortly after by Andres and Cagino, but they are still there. So in particular, there is no known such behavior, and maybe it is actually not even true. We don't know. And I'm going to focus on the other constant, on this Hausdorff dimension, on this dh, or if you want, on this constant b that appears here. So you will note that this is the power of t in this formula. So what we would like to do is to be able to identify the power of t that appears in the decay rate of the off-diagonal heat kernel estimate. Okay, so that's the goal for now. There's a conjecture or a result in the physics literature, which result of Watabiki, and if you read that paper, you might deduce that dh is this formula as written up here. And what I want to emphasize in particular that for gamma small, the dh of Watabiki is like that. Okay. Now, one remarkable aspect of this formula, which actually you do not see by what is written here, so I'm not sure what am I writing here. No, maybe it is true, right? Yeah, it is true. It's okay. This is only for gamma small. For gamma not small, actually, this is correct. So when you substitute square root of 8/3, which is this important parameter we have already seen, you get that the dimension is 4, which is in agreement with what many people in this audience are telling us. So maybe the formula is not stupid. And what I would like to think of the formula is that it should really tell us something like that. It should tell us something about the log-log behavior divided by log t. This should be of this form. This is the weakest form that you can understand this formula in the context of a heat kernel estimate. Okay, so now some results. So as I said, there are different, you can take the free field in different forms, and for some results it's easier to take one form rather than the other. So a few years ago, following a visit of Remy and Vincent in Weizmann, we looked at preliminary, or at the weakest result that we could ask. We could ask, okay, can we give any bounds? Okay? And the answer is yes, you can give some bounds. So for this particular model, never mind what it is, the result should go for more general models. We could give upper and lower bounds, which had a form of the right form. So the fact that here you get something like 1/t, as I mentioned, was already in earlier work of Rhodes and Vargas, and we got some estimates, and those for small gamma behaved in the following way. So for the upper bound, we got something like 2 + 2 gamma, so something linear in gamma, Whereas for the lower bound, we got something like 2 plus gamma square over 4. So you see a huge gap already for small gamma. And the Watabecky prediction, by the way, is quadratic, and it's 2 plus gamma square, as we discussed earlier. So first of all, the Watabecky prediction sits in between these two values, but also it's closer to the lower bound. Okay? I should say that the upper bound was improved by Andres and Cagino, but still the behavior for small gamma is the same. Okay, now I would like to make a detour and to say something about universality. So I mentioned that many of the results in for Gaussian free field and low correlated fields are universal and do not depend on particular perturbations. So, so here is a result which kind of dampens this enthusiasm, and which says that for any epsilon, I can construct for you a log correlated field. So a log correlated field means that the covariance is of this form with G bounded and even continuous off diagonal. Okay? So it's bounded everywhere, but it's continuous only off diagonal. And in such a way that you will get an exponent 2 plus gamma square over 2. So this has two consequences. The first one is that the behavior here is not the same behavior as in Watabecky's formula. So if Watabecky's formula is correct, it cannot be universal. So that's one consequence from here. The other somewhat interesting consequence is that in this case you can actually compute the exponent up to a small error. So note that I'm not claiming that the exponent is exactly that, but it's that up to an epsilon. So even in this very simple case, you do not get the exact exponent. I should add that as we will see later, for the true Gaussian free field, the behavior is different. And this tells you that really the behavior cannot be universal, at least in this sense. So
we should say that it might still be universal among the things that are conformally invariant.
So F remarks, so now we know who the F was, or who is a candidate. So, yes, so this disappeared. So, in fact, that is absolutely true. The remark of Scott is certainly correct. Namely, there may be different universality classes. Maybe if you assume in addition that the process does not oscillate like crazy as you get close to the diagonal, you do get universality. I don't know. The short answer is that I don't know. I would not want to speculate, but it seems to me weird that these oscillations, you see, if you told me that the oscillations are causing the hit kernel, the exponent not to be defined, this I'm willing to believe. But if it changes the exponent to be completely different, this looks weird. I'm not saying it's not possible. I don't have a proof that this is not the case, but it looks weird. In any case, the result is what is written. That's what we can say. And I should say that this is based on earlier results by my co-authors, by Ding and Zhang, which were looking at first passage percolation on the exponential of the Gaussian free field, which is a somewhat different quantity, but it has geometry in it as well. It has the geometry of the Gaussian free field in it as well. So this leads us to really the new results I want to advertise. So, okay, so we have all these kind of bounds, but do we know that the hit kernel exponent actually exists? What can we say about that? It's not obvious that the limit exists at all. Maybe there are fluctuations, and God knows. So before I answer this question in the affirmative, I would like to introduce another notion, which is a graph distance related to the measure. So this is a measure. So I remind you that this measure is the GMC associated with V, is a well-defined random measure. And we can define a distance based on that in the following way. Looks at balls of total mass bounded by delta square. So the mass is a mass associated with the measure. Okay? So look at Euclidean balls with mass and mu v at most delta square. And now, among all these balls, let's say with rational centers and radii, look for the minimal number you need to connect U and V, points U and V. Okay? So the name of the game, by the way, is going to be all the time, we fix U and V. We do not allow for a random choice of U and V. Maybe this changes the results, I don't know. We fix U and V, and we are trying to construct a path. So this is my U and V. And we are constructing a path. Maybe it looks like this. Okay, that connects U and V. Something of that form. Okay? Is the definition clear? And this quantity we call D. And it has two parameters, the delta, that is the mass of each ball, and the gamma, which is in the mu V. And the theorem is the following. First of all, once you fix U and V, then this distance has a limit. It's a power of delta, essentially. So the number of balls you need is a power of delta, which we denote by kappa. And second, the heat kernel exponent in this weak form also exists and is related to the previous kappa by this formula. Okay? Questions about the result?
It's consistent with the theorem that's for heat kernel.
Well, yeah, except that this is extremely weak. For example, you will note that because we took here a log, we don't discuss the distance. If in order to discuss the distance, you need to remove a log from here, put here a power of t, and show that it doesn't oscillate first on this scale. And this I don't claim, and I don't know how to do. Okay? And the third point is that, okay, this is a non-trivial result in the sense that this chi is non-trivial. So there is it's strictly positive, and it's actually bounded above by an explicit expression. This explicit expression comes from work of Scott and Bertrand. Anyway, this behavior is still consistent with Wattabicki's conjecture and with the previous bounds, so there is nothing here that contradicts those bounds. Questions about the... Okay. Yes.
Is it possible to relate these type of distances to something with like growth model, like these type things that grow from the time it takes or something like that?
So there will be a talk, I think, but at least there's a paper that relates this exponent, or the paper of Ding and Zhang that relates this distances to a lot of other distances and shows that it's the same exponent that appears. And once you have that, and I don't know if this particular gross model is in there or not, I've not studied that yet, but yes. So this exponent is kind of appearing everywhere. It's not an accident. And it's not an accident that these two are related. Okay, now one remark is that once you have made the relation to D, to this distance, there's an earlier result of Ding and Goswami, which showed that for gamma small, the behavior is not quadratic in gamma. In particular, it's gamma to a power 4/3, which is between the linear and the quadratic. Okay? And this tells us that, at least for gamma small, Watabeke's formula cannot be correct. At least if you interpret it in the way that I interpreted it here, namely either as a heat kernel exponent or as a distance exponent. Okay? It also says that it's very good that when we try to do the upper bound, we were trying for a long time to do a quadratic upper bound, and it's very good we didn't succeed. Okay. So there are related works, and in particular, this is a paper I was mentioning earlier. Okay.
What was the last sentence? Very recent.
Yeah, it's the one that I mentioned in answer to the question of Wendelin. Namely, they relate these exponents, this chi, which I think they call D now, to different models. But you shouldn't ask me about it. You should ask them.
Close to Watabe.
Sorry?
Now it is very close to Watabe.
It's very close, but it's not true for small gamma. It's very close for all gammas. It's not identical because they only have upper and lower bound, which are obtained in an extremely clever but crude mechanism, so it doesn't actually give an answer. It's very close. It's, I don't know, 10%? What is the gap? I don't know. Sorry?
It's off by about 0.1 from Watabe on either side.
Oh, voila. So it's really close, but okay, who knows? There's no proof that Watabe is correct or incorrect. It's clear that if it's correct from some point onward. It's not clear if that point has any meaning. So there are lots of puzzling questions. Okay, now I wanted to give you a sketch of some proof ideas because essentially each and every paper in this sequence had different ideas, and okay, some of them were related. So first, I'm going to discuss now the lower bound because it's where it's easier to explain. So the lower bound in the paper with Pascal, Remy, and Vincent was using a representation in terms of a bridge formula. Namely, you can integrating the heat kernel is the same as integrating the ordinary heat kernel, but with a conditional expectation with respect to a Brownian bridge of a function of the time change. And in particular, this gives you a formula for the resolvent. Now, if you know resolvents, that you know then immediately, if you know well enough resolvents, and in particular the asymptotics for large lambda, you get heat kernel estimate at least integrated, and then with a little bit of Harnack, you can transfer it to pointwise bounds. So this is what was done, and now the key estimate is to try to understand this kind of expectation. So you have here the time change that comes from the Liouville factor. And the strategy in that paper, that's really the only takeaway that I want you to take, was extremely crude and extremely stupid. Namely, you take a straight line. Since we are dealing with lower bound, we can force the Brownian motion to do whatever we want. So we just force it to go along this straight line. Along this straight line, there are regions with, so the probability of that, it's computable. It's just a probability for a Brownian bridge to stay confined. Then along this, there are some boxes. So those boxes, I didn't write it here, but they are T by T boxes. And along this line, there will be boxes which are thick, which has a certain level of thickness. And we know how many such boxes there are. So, and now, when you traverse each box within time t, we know more or less how much Liouville time change you will accumulate. It's just the crossing time times the value of the field, which is determined by the thickness. So if you want a atypical behavior, which is to go from x to y in short time, what you can do is force your Brownian bridge to go fast, to accelerate. So every time it hits a thick box, you just force it to go faster. It has a certain cost, you accumulate the costs, and you get the estimate. Okay, so I don't want to give more details than that. Now, of course, it's clear that this cannot be the right answer, because we didn't do any real work which has to be a percolation work. It has to look for channels in which it is easier to go fast. So, so now let me describe to you again quickly this class of fields that I said log correlated, but for which the exponent is not the one you would expect by Wattabiki or whatever. And these are modification, so you should really think of it. You can think of the Gaussian free field as being built in layers. And each layer is a dyadic, so the logarithmic, so if you are looking up to a certain scale, those logarithmic number of scales, each one independent from the other, and in each one the field is essentially local at scale 2 to the minus n. Okay? So that's roughly what Gaussian free field is. Now, what you can do instead of doing that is skip every k scales in this dyadic thing and increase the variance. Okay? So it's easy to check that you will still have a logarithmic structure, but now the field is somewhat more regular than the Gaussian free field. It has less variability across scales. And so this is explicitly what one is doing. It's a continuous version of modified branching random walk. And this function, which is a distance from the log, is bounded. Of course, it depends on how many scales you jump between each time. So this is this function. And now you can divide your field, and these names are going to be important. You can divide your fields into two, what we call the coarse field, which is a field that is relatively regular up to scale r, and everything that happens below it. Okay, so this is a coarse field, and everything below is what we call the fine field. And when you are looking at a fixed scale, typically the fine field is something that will not affect integrated quantities at that scale. So that's what we are doing here. And then the main lemma is that you can find a path of boxes on a particular scale, and such that in each of these boxes the coarse field is not too large, so this integrated field on the scale of the box, and the fine field is not too bad. Namely, if you take a Brownian motion, so it starts and ends, remember that the Brownian motion, the path of the Brownian motion is not affected by the field. So it's something that is telling you about something about randomly sampling points in each box. So if you randomly sample points in each box and you let the Brownian motion do the crossings, the time change will not be too bad. So this is what it means. And yes?
Is that a variation on the Euro percolation,
yes.
fractal percolation story?
Yes,
right?
yes, it is. It's a technically lifting variation, but yes. And once you have that, then the rest is more or less routine. And the upper bound is complementary in the sense that you cannot do better. You cannot find something that consistently will have boxes that go fast, because that's expensive. Okay, now what about convergence? So the main idea is to somehow, of course, if we are doing convergence and not giving you formulas, either you do a Cauchy argument or you do subadditivity. We do subadditivity. And the basic idea is the basic idea is the following. If we want to do that, we would like to claim that if we go from scale delta, so suppose we want to go from scale delta to scale delta times delta prime. Okay? So this means we want much smaller balls. What we would like to claim is that somehow, if you told me that this ball has mass delta or delta square, when I want to look at balls which are delta times delta square, I can further subdivide it and find inside the best path, inside this little box. And unfortunately, when you define the delta box here, it depended on the whole field, on everything inside the box. So the first step is to decompose, and maybe here I should go to the board, because this would be too. So maybe the 0th step is to write the GFF. We can rewrite as an integral of P T V or T half R X Y W of dt dy Okay, sorry. Well, this is a usual hit kernel. PTV is just a hit kernel killed when exiting. So I forgot to mention we are working in a box V, which is just a unit box, and we are taking the free field, which corresponds to Dirichlet boundary conditions. Again, nothing that I'm saying should really depend on that. So this is a Gaussian free field. It will have the covariance, which is a green function with Dirichlet boundary conditions. And now you can do all sorts of approximations. So in particular, so this integral is for time going from 0 to infinity. Of course, large times are not important because of the fast decay here. So it's essentially the integral from 0 to 1 or to a constant. And this integral is over V. Now, we can define an approximated version, and in general, an approximated version will have integration from delta to delta tilde in time. So this will be the scales between delta and delta tilde of the same quantity. And instead of delta tilde, we will often, if we write infinity, this will be also an approximation, then we will not mention delta tilde. Okay? So this field is going to be an approximation for that field up to scale delta. And finally, in order to get easier percolation type arguments, we would like to replace this PT half by an integral where here we look still at PT half, but we don't look at V, but rather we look at V intersect with a ball of radius s to the 1/2 log 1 over s and V. So, of the same quantity. Okay, this is xy. So there are two steps of approximation. One, I only look up to scale delta. And second, for times that are much larger than the exit time, I truncate the, not time, for distances that are slightly larger than what typically happens at time s, I truncate the transition probability. Okay? Yes? Yes. So this has the effect of localizing and creating more independence between the different ethers in different boxes. Okay? And now we can define an approximate measure, which I will call m gamma epsilon. So this quantity I will call eta delta. This one here. And this will be simply epsilon squared times e to the gamma eta epsilon of v minus gamma square over 2, the variance, the expectation of eta epsilon square. Now, and v, this is m gamma of a box, and v is the center of the box. Okay, so I'm doing one last approximation. Instead of really integrating the measure, after I've regularized the field is not too wild, so I can take just a point, the center of the box. Okay? And that gives me an approximate measure, which is defined on boxes. And now I can define a distance, a new distance, which is defined as follows. So now I'm only looking at such measures. And what I can do is I can begin with my box V and begin to subdivide it until the measure according to this thing where epsilon is replaced by the side of my box is smaller than delta square. Okay? Is that clear? So instead of taking m to define my balls, I'm now not looking at all balls, I'm doing divisions, and I'm further subdividing things according to this measure. Okay? So I got myself so if I fix a delta, I got myself eventually a partition such that each of the boxes has this approximate measure at most delta square. Okay? So let's call this distance d prime. And this d prime is, of course, d prime of gamma delta of xy. So this is the distance, how many such boxes you need in order to connect x and y. And the main technical result is the following estimate. Actually, it's worse than what I'm going to write, but to simplify, so the main technical estimate is simply that d gamma delta of xy is bounded between d prime gamma delta of xy times e to the minus log delta to the 0.9 of the same quantity e to the plus with high probability. Okay? So I of course don't have time to explain how exactly this is done, but once you have an estimate like that, because of the properties of localization of this d prime, you can hope to use a subadditivity, because the important thing is that the d prime has not looked inside the boxes. It only uses a white noise at scales delta or larger, or in this case, the side lengths or larger. In particular, when we move from delta to delta times delta prime, we need to look at all the scales smaller. Those we have not seen yet. So whatever the multiplication factors that we will get, it's going to be independent of the partition we have done so far. Okay? So that's the basic idea. I'll stop here.
What did you have in the next 4 slides?
Yeah, the chairman allows me. Yes, I just have to find the clicker. Or did I do this? Okay, so it's saying in words, so this is the integral, so you recognize here the representation of the GFF. You move to dyadic grid, localize, this is, so by localize I mean exactly this kind of operation. And then there are a few more ingredients which I add here. So one of the difficulties that you have to fight is that when you are dealing with this kind of partition, it is possible that next to this box, the neighbor is going to be tiny. It's possible. It's unlikely, but it's possible. And if this happens, this causes a lot of problems, because all our factors of control depend on delta, and if the delta here and delta there are different, it's a catastrophe. So you have to control such situations, and this is a headache, but basically what you do if you're faced with such a situation, you go around. So you have to show that you can do interpolation argument and go around. So that's it. And then you apply subadditivity, as I tried to explain here. And finally, to get to the Brownian motion, you use an argument not dissimilar with what I said before. Namely, once we have already this geometric path, the independent Brownian motion that is going to move there, you have only to show that somehow most points are not too bad, in the sense that you're not going to have very irregular fields, and the Brownian motion is not going to pick up these particularly bad points. Okay, and then there are more details, and there is another slide of even more details, but maybe I'll show them to you separately.
Other question? Just returning to Watabe-Ki, so where could the Watabe-Ki play any role?
I have no idea, I don't know.
Is there any space where it could be?
I don't
Any
know.
other definition of distance? Any other definition of the dimension with where it could play a role? Apparently you say they are all equivalent.
Yes, so no, there are two separate questions. The first one is Watabe-Ki formula correct? And this, who knows, these gentlemen are showing bounds that are pretty close, but it doesn't say that it's equal. We know it's not true all the way. I don't know. And but on the other hand, what they are showing is that different distances are really the same. So it's not that there is a hope. I don't know. I really don't know.
But there was also a numerical study by Budd and Ambion, where they looked at the torus, where they could somehow fit the dimensions to Watabe-Ki's.
Yes.
Of course, that's numerical.
Yes, but the result is that the differences are, I don't know, tiny. So I'm not sure that the numerical analysis can detect such tiny. I don't know.
Numerical data fits really nicely into their new bounds.
Yes, yes.
No contradiction.
Yeah, so it's really, I don't know.
Thank you again.